Welcome back to Mastering C++ 20 Features. In the last lecture, we looked at requires expression. In this lecture, we will look at the issues related to overload resolution when two generic functions are constrained with different requires clause, and later in the lecture, I will show the difference between simple requires expression and nested requires expression that are documented in CPP reference page on concepts and type constraint, and show you how to leverage the feature of nested requires expression to create stricter requirements. So let's begin. First, I would like to convert the requires expression for the two overloads of add1 that I created in the last lecture to a named concept. If we recall the syntax of the named concept from previous lecture, a named concept has the token template type name T, followed by the keyword concept, name of the concept, equal to sign, and on the right hand side of equal to sign, the requires expression. In the body of the requires expression, we specify the constraints. So let me convert the requires expression in the previous code from the last lecture to a named concept. Let me switch to my code editor. Here's the code from the last lecture. Let me hide the console. And let's start creating the named concept. I can call the named concept for the first overload of add1 as numeric type. Here I can copy the requires expression from the first overload of add1 and create the named concept out of it. For example, template type name T concept and call the name of the concept as numeric type equals to requires keyword, parameters of the requires expression, which is param of type T, and then the body of the requires expression. And in the body, I can simply copy the expressions from the previous requires expression. Don't forget to add a semicolon at the end of the concept definition. Also, I would like to change the last requirement a little bit. Namely, I would like to change the std is convertible underscore v type trait expression to std is arithmetic v, keeping the template expression unchanged. Let me just type it. And I can get rid of this requirement. So this requirement suggests that the type of param plus 1 should be an arithmetic type. I could have as well used this. Alright, I can create the named concept of the second overload of add1 and call it pointer type. So this can be done similarly. Template type name T concept pointer type equals to requires parameters of the requires expression and the body of the expression. I can use the type trait std is pointer v. This is similar to the requires expression for the second overload of add1 method. And like previously, I would like to add one more requirement in the body of the concept pointer type. Namely, the parameter param can be compared with a null pointer. This can be done like this. Param equals to null ptr and semicolon. This makes sense since all the pointers can be compared to null pointer. Note I can type either equals to like I've done here or not equals to. The requirement doesn't imply that this expression has to evaluate to true, but simply enforces the check that param can be compared to null pointer either by equal to or by not equal to sign. Either of them works fine. This is just a check that the comparison works. And in the end, don't forget the semicolon again. I can use this named concept in the requires clause by simply getting rid of the requires expression and replacing them with the concept name followed by the template parameter t with an angle bracket. Let me show you how. For the first overload of add1, I can get rid of the requires expression And here I can simply use the name concept followed by the template parameter within the angle bracket. Similarly, for the second overload of add1, I can use the concept name pointer type with the template parameter within the angle brackets. I can tell you that this code will not compile and we will get same ambiguity in resolving the overload resolution. Let me show you by compiling the code. Let me pull this up and clear the console. And here we get the ambiguity. Call of overload add1 int star is ambiguous. It tries to find the overload in line number 23, which is the numeric type, and then finds another overload which matches the call, which is in line number 32. There are two reasons for this, which I will shortly discuss in detail. One reason being that the call to add1 mysteriously matches both the constraints numeric type and pointer type overload, and somehow the constraints in the body are not working the way we intended them to work. Which leads us to the second reason. Like I mentioned before, in the case of equality comparison of param with null pointer, compiler only checks that the expression are valid, and it does not evaluate the expression. That is, none of the expressions in the body of the requires expression are being evaluated to true. The compiler simply checks that it can use the template type name parameter here, and the result can be either true or false. It doesn't care about the value of true or false within the requires expression in the name concept. To understand how to resolve the ambiguity in overload resolution, we need to understand how the overload resolution actually works when template parameters are constrained. While defining generic function overloads with different constraints, we must keep the following rules in mind. The rules specify the following. The first rule is very straightforward. The compiler prefers constraint function over an unconstrained function. Second rule states that if an overload matches the requirements of a given template parameter, then call it. Here we can think of two cases for function with multiple overloads. Constraints with no overlap in requirements depicted by the first picture on the left, and constraints with some overlap shown by the picture on the right. In both the cases, as long as the constraint matches the requirement for a template parameter for a given call to a function, the overload resolution is successful. For example, in the case of our constraint numeric type and pointer type, the constraints were mutually exclusive. But we can also specify constraint pointer type to satisfy that the template parameter should not be a Boolean type, and then we have an overlap of the constraint specification for pointer type and numeric type. In this particular case, the new requirement in the concept pointer type doesn't really make a lot of sense, but it was only for clarifying what could overlap in the requirements between two or more constraints can mean. With that being said, there's no harm in specifying as many requirements as possible, but this will increase the compilation time in program, and in production code this is not desirable. And we should in practice think about the most important requirements for a given constraint that we want to formulate. Okay, let's check the third rule now. If the overload resolution matches the requirement of template parameter with two or more constraints, then the compiler checks if one constraint is a superset of the other. This can be shown by the picture on the bottom right. Here constraint A is a subset of constraint B. All the constraints specified in constraint A are specified in constraint B, plus constraint B has possibly more requirements than constraint A. In other words, constraint A is a subset of constraint B, or simply said, B is more constrained than constraint A. In this case, the compiler will call the more constrained overload, which in this case will be an overload with constraint B. If both the constraints have the same requirements, then the overload resolution fails and compiler complains about ambiguity while trying to decide the correct overload for a function call. This is exactly what happened with us when we specified two overloads of add1 with constraint, numeric type, and pointer type. This might seem surprising because we specified different requirements in each of the concepts. Then why could the compiler not decide which overload to select? By the way, all the rules that I mentioned about overload resolution for functions with different constraints on template parameters can be found in this website. Alright, let's get back to our problem with the overload resolution for our add1 function. The reason for the overload resolution failure in our case is that the requirements within the concepts are not evaluated the way we expect them to. If you recall my previous point about the requirement in pointer type concept where the expression param equals to null pointer is specified, this one, and that the compiler only checks that this expression is well formed and not that this expression is true. This is exactly what is happening to all the requirements in both the constraint, 1 being here and 3 being here in the numeric type constraint. The compiler simply checks if it can evaluate the expression specified within each of the constraints and does not care whether the result of evaluation is true or false. For example, if we naively try to compile and print the result of std is arithmetic_v with a template parameter as pointer to an int, or std is same_v with template parameters pointer to float and bool, we will see that the code compiles because both the expressions are well formed, but the results in this case is false. Let me show you by simply writing this expression in the code itself. I have copied the code in my clipboard. And here, the first expression std is arithmetic_v has the template parameter which is pointer to an int. And since this expression is well formed, the compiler will compile this code only that the result of this code will be false. And similarly for std is same_v with template parameters boolean and a pointer to a float. To compile this code, I'll first comment out the code above so that we stop getting compilation error. And now here we see that the compiler compiles the code and we get false printed on the console. Similarly, for the call to add1 with pointer type, the compiler substitutes t in both the constraints only to find that the expressions are well formed, and it can evaluate the type trait specified in requirements in both the overloads. That is one being here, the template parameter t, which is a pointer to an int called from here, is substituted during constraint overload resolution, and the compiler can evaluate this expression and this expression. Similarly, when it tries to substitute the template parameter t in the numeric type to see if the requirements are satisfied, it finds that these expressions can also be evaluated. And therefore, the compiler doesn't know which overload is more constrained. And hence, we get a compilation error about the ambiguity in overload resolution. What we want in reality is that when the compiler checks for the overload, most of these expressions, especially the type trait expressions, are evaluated to true. And if not, then the compiler looks for another overload. And if it cannot find another overload as well, then the compiler should throw an error about ambiguity in overload resolution. This brings us to understand the difference between simple and nested requirement, which we saw in the CPP reference page a few lectures ago. I will discuss more about this in the next lecture. So stay tuned and enjoy learning modern C++. Thank you. Hello there. If you enjoyed watching this video, don't forget to hit the like button and subscribe to my YouTube channel. If you have any questions or if you would like to start a discussion on the topic covered in this lecture, please feel free to leave a comment on this video. And lastly, if you are interested to learn more about my courses, then log on to my course website, mastering-modern-cpp-features.thinkific.com. Thank you.